Good afternoon, everyone. It's a pleasure to actually see a room full of colleagues and students excited about a wonderful presentation. So I promise not to take very long because I'm not the guest of honors here. We're actually delighted to have Professor Michael Levitt joining us. In fact, he was very impressed by the well-attended room, and he promised to come back. So we have to make sure he has a wonderful experience with us today. So it's my great honor to introduce our esteemed speaker today, Professor Michael Levitt, a distinguished figure in the field of computational structural biology and chemistry. Professor Levitt is currently the Robert W. and Vivian K. Cahill Professor in Cancer Research at Stanford University Medical School, where he has been a faculty member since 1987. He also holds an appointment as a professor of computer science at Stanford University. Professor Levitt received his Bachelor's of Science degree in physics from King's College in London and his PhD in biophysics from the renowned MRC Laboratory of Molecular Biology and Cambridge University in 1971. Over the years, Professor Levitt has made significant contributions to the understanding of molecular structures and interactions, particularly through his pioneering work in developing multiscale models for complex chemical systems, for which he was awarded the Nobel Prize in Chemistry in 2013, alongside Professors Martin Karplus and Ariel Worcel. His extensive research portfolio includes over 160 publications on a wide array of topics, including RNA and DNA modeling, protein folding simulations, antibody humanization, and the intricacies of molecular dynamics. Professor Levitt's innovative approach have led to practical applications in modern anti-cancer therapies, including the development of critical methods for antibody design. Beyond his research, Professor Levitt is a respected member of various prestigious organizations, including the US National Academy of Science, the European Molecular Biology Organization, and the Royal Society. He has served as an editor for a number of prominent scientific journals, including Molecular Biology and PLOS Computational Biology. Today, we are privileged to hear from Professor Levitt about his personal scientific journey and wonderful insights into the fundamental processes that govern life at the molecular level. Please join me in warmly welcoming Professor Michael Levitt to the stage.
Thank you so much. It's a great pleasure to be here. An amazing crowd, very exciting. And as John has said, I'll be talking about my life in science with an emphasis on various things that I've done. So basically, I'm going to start out about how modern biology began. I should also say that I spent a lot of time in China. My wife is a curator of Chinese contemporary photography, but I also spent a lot of time in the United Kingdom, as John said. And as such, this university is a wonderful combination of two very important parts of my life. So I'm going to first start out by telling you about how modern biology began. And it was really interesting because it began with a small group of people in Cambridge, England, in the 1950s. Einstein is said of, well, there's a saying that one should stand on the shoulders of giants. And I think in science, as everything else, we always stand on the shoulders of the people who have come before. It's very important to acknowledge that. Some people think you shouldn't acknowledge the work that went before, but that's a really, really bad mistake. So in my life, there were three scientists, maybe even more, who played a very, very important part. One was John Kendrew, a scientist in Cambridge who solved the first structure of a protein. the protein myoglobin, which comes from the muscles of whales. It was very, very hard to make protein in the 1950s, and whales were still being hunted for their meat, and whale meat has a lot of protein in it. So Kendrew basically solved the structure of myoglobin. There's a picture taken from the cover of Scientific American. Scientific American, which is a popular journal, teenagers would read it all around the world, was very, very important back then because it was the only journal that published in color. So Nature, Cell, and Science were unimportant because they were just black and white, whereas Scientific American was where you put your first result, and you see that picture of a part of myoglobin. It's so complicated that without the color, it would be even impossible to see. And Kendrew basically solved the structure of myoglobin using a method that had been developed by Max Perutz. Max Perutz was Kendrew's supervisor. He decided to work on a more relevant protein than myoglobin from whales. He wanted to work on hemoglobin in our blood, very important protein. It makes our blood red, and it carries the oxygen in the blood. And one of the major roles of blood is to bring oxygen from the lungs to where it can be used all around the body. Now, hemoglobin is actually 4 times bigger than myoglobin. And this meant that Kendrew solved his structure about 10 years before Perutz solved his structure. And in fact, when Kendrew solved his structure, Perutz hadn't solved his structure. Although he actually used Perutz's method, Perutz wasn't on the paper. Because this is now the 1950s, there's been terrible depression from the 1930s, World War I in the 1915 to 1918, big depression, another war. There was a great depletion of talent. And these scientists realized that we needed to make young people independent. Okay, so basically, Perutz was the head of the laboratory in Cambridge. In that laboratory, there was also a PhD student, Francis Crick. Almost everyone in the world has heard the name of Francis Crick, like almost everyone in the world has heard the name of Albert Einstein. These were 2 of the great geniuses in science in the 20th century. And basically, what's interesting about Crick, he solved the structure of DNA. He predicted the structure of DNA. He did it actually using this image. This is an image that was taken from work that Rosalind Franklin had been doing. And this image was shown to Crick by Perutz. So Perutz actually, sorry, I need to get this direction right. Perutz actually shows Crick the picture, helps Crick publish the paper in Nature, but his name isn't on the paper. In Crick's paper, it's Watson and Crick, Perutz isn't there. Now just think what happens today. Imagine a student has now done the most important work. It's almost unthinkable that his PhD supervisor wouldn't put his name on the paper, especially when the supervisor provided the essential evidence that allowed the structure to be determined. But this is also because Perutz felt that it was really important to encourage independence. Okay. This just says the same thing, but you don't need it. I guess all my slides have a lot of English and Chinese. Most of the Chinese is thanks to ChatGPT. And so far it seems okay, but I'm sure it's not perfect. Okay, so these great scientists basically revealed how physics and chemistry provide the secret of life. Essentially, the secret of life can be summarized on one slide, where the information in DNA gives rise to a 3-dimensional structure of a protein. That protein has some kind of function in the real world. For example, in my example, the protein is eating food. It's cleaving a molecule which gives energy. That is good for the cell. The cell grows, the cell multiplies, and we have more copies of the DNA. So it's a very, very simple learning feedback loop. But this is essentially how all life works. Now, if you think about it, the hard step here is how you go from the information in the DNA, which is a 1-dimensional information, to a 3-dimensional structure. And we'll be saying a lot more about that. So we have DNA, and DNA is a double-stranded molecule. You can see in the middle picture there's a red strand and a green strand. sometimes called the Watson strand and the Crick strand. The important thing is that the DNA bases are not identical. When you see the picture on the left, they actually look very similar, but they actually are slightly different by about 1 atom out of 30. But 1 atom is enough to make a significant difference, and therefore you can code information in the order of these different nucleotides along the strand. Proteins are made from the DNA. We'll say more. Proteins are also chains. So we take the sequence of the DNA and make a sequence of amino acids using the genetic code. We have 4 code letters in the DNA and 20 different amino acids. With 4 letters, you could actually make you could make a code of 64, but we only use 20. Now, the protein is a long ribbon. The ribbon has more structure. If you look at the colored ribbon or the colored necklace below, some of the amino acids are big, some are small, some are positively charged, some are negatively charged. Some are soluble, some are insoluble. And it's these properties that make proteins into a magic substance. Essentially, the protein, which is long, actually folds up into something that's compact. And this compact object has a well-defined 3-dimensional state. So because the protein folds, we've gone from a 1-dimensional thing into a 3-dimensional thing. And a protein is probably most similar to the kinds of knots, very elaborate knots, that we sometimes find in Chinese artwork. They're not knotted, generally, but they're folded up. And the important thing is that fold, which sort of looks random, isn't random at all. That's a small protein called bovine pancreatic trypsin inhibitor. We all have it, or something very similar to it, in our gut. Trypsin is an enzyme which dissolves protein. But we're also made of protein ourselves. So we have to control the trypsin inside us very, very carefully, and that molecule helps to control the protein, the trypsin. So this molecule has a well-defined shape, and that's very, very important. Okay. So crystallography that Perutz had developed gives us the structure. But in fact, proteins change. They move. So we need to get the motion and the function, and that is where I basically came into the story. So computational structural biology begins, and this is now we're talking about the late 60s. So I tell people I've been writing computer programs for almost 60 years. It's almost true, maybe 58 years. Okay. And again, Kendrew, the person I mentioned at the very beginning, who won a Nobel Prize in 1962, was really important in my own personal life. I grew up in South Africa. And for various reasons that I won't go into now, I skipped a couple of years of school, started university when I was 16 or 15, and did 1 year university in South Africa. I'd been working very hard for about a year. My mother, as a reward, sent me on vacation to England to spend 3 months with my uncle and aunt who were there, both of whom are well-known scientists, were well-known scientists. Now, for me, the important thing was not that they were great scientists, but that they had a television set. At that time, there was no television in South Africa. I saw television and was immediately hooked. I was watching television non-stop all the time. And basically, luckily in those days, there's only one channel. So you didn't have to watch the right channel. And very fortunately, John Kendrew won his Nobel Prize in December 1962. And at the beginning of 1964, I went to England in November 1963, just a few days before Kennedy was assassinated. I remember hearing about it on the tube in London. And Kendrew decided he would make a BBC film, TV, describing molecular biology. He called it the thread of life because all biological molecules are threads, like in Chinese knots. And the talk was actually amazing. It was about the revolution in biology, inside the cell, proteins in 1 dimension, proteins in 3 dimensions, and so on. And this is in 1964. Now, I was very lucky. I saw this program. And immediately I decided that I was studying mathematics in South Africa, that I really wanted to study molecular biology. And therefore, my uncle and aunt said, well, if you're going to do this, why don't you get into the English system right now? Do your A-levels, because in South Africa, the educational level is so low that you finish school at O-level. And you need to do 2 more years to get into a British university, 3 more years to get into Cambridge or Oxford. So I decided to do my A-levels. It took me a few months, and I didn't do chemistry because chemistry required remembering things, whereas physics and mathematics, you could sort of guess the answers. In chemistry, you cannot guess the answer. And in biology, it's very, very hard to guess the answer because of evolution. Anyway, basically, I did my degree in physics, again, choosing physics because it's kind of between mathematics and chemistry, and again, relatively straightforward, at King's College in London. Chose King's College because when Crick won the Nobel Prize with Watson, Wilkins was also there. And Wilkins was the scientist who supervised the lady who got that great photograph that Perutz had shown to Crick. But she had died, and Wilkins got the Nobel Prize as the third person. So basically, Cambridge was very close to King's College. I didn't want to spend an extra year doing S-levels to get into Cambridge. Got into King's College, studied physics, did quite well, and in my third year of physics in 1967, decided I wanted to go to Cambridge. I wrote to Kendrew. Remember, there's no email. You have to write letters, and they take days and days to come. And he wrote back saying, well, they weren't actually considering any people that year, or we weren't considering any new people. So I was also, I'm all the time going to be saying this, I was very lucky, because my life is full of luck, and you might argue that anyone who's successful was lucky, but I think anyone who's alive was lucky, because there's so many ways you can die. And I imagine a big multiplier, 1 minus p, to a very high power can be a very small number, and we're lucky. Anyway, I had friends who were in the business school in King's College, and they said, if somebody tells you that they won't take you, you don't just say, okay, you make a counter offer. If someone won't buy what you're selling, you come back with a different price, a different quantity. So they said, make a counter offer. So I had this great idea. My counter offer would be, if I can't come this year, can I come next year? Big deal. But that actually made a difference. And they said, okay, no one's ever said that to us before. Maybe you'll come and be interviewed. So I went up there, and I met with Crick and Perutz and Kendrew and all these guys, and was completely blown away. But when they wrote back to me, they said, well, we really liked you, but we'll tell you next year if we accept you next year. My friend said, you've gained nothing. I mean, you still don't know what you're going to do with your life. So anyway, through a lot of negotiation, Kendrew said he would take me next year, provided I went to Israel for the year in between. Now, I didn't have any particular affiliation to Israel. I'm Jewish, and Israel had just won the 6 Days War. It was in the news. But he wanted me to go to Israel. And it took me many years to understand why he wanted me to go to Israel. And basically, he realized that the same interactions that stabilize proteins are exactly the same interactions that stabilize small organic molecules, crystals, complexes, and so on. And in Israel, there was a man who was actually working on this. So there's an example. By 1967, a second protein had been solved, lysozyme, by David Phillips at Oxford. And we now had 2 proteins, but in each case, the arrangement of atoms satisfies the laws of stereochemistry. So he basically sent me to work with a man called Xi'an Jiaotong-Liverpool, who passed away in 2001. We both looked a lot younger in the late 60s. And basically, he was working with his PhD student, Arya Varshil. Arya actually shared the Nobel Prize with me because he was still alive. And basically, he was working on what they called the consistent force field. The idea is you need to have an expression for the potential energy of a molecule. If you know a little bit of classical physics, potential energy is the secret of everything. If you have the potential energy, you can calculate the dynamics, you can calculate the frequency of occupation of different states, etc. It's the driving equation, and it's a simple scalar equation. The energy is a simple number, not a vector, at any point in space. So basically, and again, for those who want to read, just to make sure that I said the right thing, it's there. So basically, and again, I just said the same thing, there's a picture of showing what an energy function looked like, a classical energy function. Remember, quantum mechanics really describes the energy function of a molecule. But quantum mechanics is really expensive to calculate. And even today, when computers are probably 10,000 million times faster than they were in the 1960s, we still have difficulty doing the calculations. So the idea was to treat a molecule as a bunch of balls connected by springs. And you have the bonds and angles that are springs. You have twisting functions that are periodic. You have van der Waals interactions where all atoms attract each other. And then you have electrostatics where positive and negative charges repel each other, but a positive attracts a negative, and a negative attracts a positive. Very, very simple. And the idea was to use a function like this on small molecules to determine the value of all the parameters. I quickly realized that what we were doing on small molecules could also be used on proteins. So I wrote the program for Varshil. I was essentially his programmer. Basically wrote the program which very quickly allowed us to minimize the energy of a protein. And this led to my second paper. And this was actually my first paper where I did the work, but the second paper where I got published, that I actually did with Lifson in that gap year, where I showed that you could minimize the energy of a protein, the protein was stable, and this energy function would describe the interactions. Now, I, in retrospect, realized that Kendra had sent me to Lifson so I would do this. But no one ever told me to do it, and it was just all luck. And the way it really happened was that I finished the work with Varshil in about 4 or 5 months, and had nothing to do in my year in Israel. And then I discovered that some of the scientists there had bought the model pieces, the metal pieces, to make a model of a protein. And making a model of a protein is a lot of work. You have to tie things to metal rods and so on. But I spent about 3 or 4 weeks making a model of the protein lysozyme from the coordinates. It's about 1,000 atoms, many coordinates to measure. And while I was doing this, I kept on thinking, can't the computer do this? Why should I have to do it? And that's what led me to basically put the molecule into the computer. Again, luck. I think I was poking around in a cupboard and found the molecular modeling pieces. Okay. Another paper that I actually did about the same time was to make a model of transfer RNA. And this was actually done immediately I got to Cambridge. After my year in Israel, I went to Cambridge, sort of felt that my PhD was in the bag, started to get interested in other things. And at that time, they were talking about transfer RNA, which was the smallest RNA that seemed to be interesting, 76 letters. And that's sort of very current because yesterday the Nobel Prize was given for medicine for microRNA, which are pieces of RNA, thank you, pieces of RNA that are actually just 15 letters long. tRNA was an important molecule, you'll see why in a bit, and I did some work on it, and Crick actually helped me get it into Nature. It actually took 22 days from submission to publication, and this is at a time when there's no internet. The proofs were actually sent to me by telegraph. Crazy. Anyway, so just to continue, sorry. Then I did my PhD, a few papers, came back to Israel to do a postdoc with Varshil, and really started to do what we called multiscale modeling, which basically was something that Einstein was said to have said, but he didn't actually say it. And one thing I should tell you, when you check quotations on the internet, ask GPT if they're real quotations or made-up quotations, because about 3/4 of the quotations are made up. I mean, somebody said it, but it wasn't the person they said who said it. So Einstein is said to have said, everything should be made as simple as it can be, but not simpler. And that's actually a very profound thing, because every endeavor has a certain scale. If I just say that my arm is moving, but I'm saying that my arm is moving by a few joints, that's a good, maybe 100 joints is a good scale. But if I said my arm contains, I don't know, 10 to the 25 protein molecules all moving, or 10 to the 25 atoms, that's a crazy description. So the right level is very important. And we used 2 levels that were interesting. One was a coarse-grained model, where we made a protein structure very simple, so it could actually be calculated and folded on computers 1975. And this I did with Varshil. It was actually published in Nature in 1975. The next thing we did was to make proteins more complicated, because the lysozyme had been solved as an enzyme, and no one really understood how lysozyme worked. People thought it was due to physical strain, that the enzyme pulled the substrate, but I had shown during my PhD that the enzyme is too soft. to pull the substrate, in the same way that a piece of sponge rubber can't break a piece of wood. You have to have steel to break a piece of wood. Varshil then helped me introduce quantum mechanics, and we added a few atoms were quantum mechanical, the other atoms were classical, leading to a hybrid approach. Okay. Then basically we got to, this I think will start. Yeah, so this was a movie that I made on protein dynamics. This movie was actually made in 1978. Each frame of the movie was $100,000 of computer time at a big, big computer at the National Institutes of Health. And the movie has 22 frames a second or 25 frames a second. Very, very expensive. In fact, the person who wrote the algorithm, let me go back, that's enough for that movie. We'll come on to other things. The person who wrote the algorithm actually founded Pixar, one of the very first animation studios. Okay, there it is again. Okay, and the molecule is moving in a strange way. I'll say this while it's actually moving. The movement is very interesting because it's not waving like a tree. If you ask what real object does it look like, it's quite hard to think of anything that looks like that. I think to me it looks like sometimes you see worms in a bag, and it looks like a bag of worms because they're moving, but they aren't actually going anywhere. The simulation was done in vacuum, and the one water molecule inside is coming out. Okay, enough. Okay, so basically, we then decided to go on to doing dynamics in water. This took a lot of time. Sorry. We're going to have difficulty with this. I can't make a key push. I have to be able to press the mouse.
What do you want?
Push the mouse. Okay, it's moving. Yeah, thank you. So basically, this is now showing a protein in liquid water. Adding water made the calculation, it's actually just an alpha helix, made the calculation much, much more difficult. It took the fastest supercomputers in the United States time to do it. And this is just work showing that the alpha helix, which is a part of a protein, is stable in water. In a bit, the scene is going to change to the same molecule at high temperature, and you'll see that it actually breaks apart. Again, common sense, real proteins break apart at high temperature. And we'll see that very, very soon. Now it's unfolding, and it comes apart. And this is something that had never been seen. I actually showed this movie when I gave a lecture to Linus Pauling, a very, very famous chemist. And it was very exciting for me to do that. Okay, very expensive calculation. Now I'm going to talk about more recent work perhaps in the last decade, of simulating the biggest and most important machine in biology, the ribosome. This is the machine that takes the chemical order of letters in the DNA and translates it into a chemical order of letters in protein. And I just said that. This is now a video. So basically, this is just a cartoon where you see the DNA or the RNA on the bottom as a straight line. And we're going to use tRNA to bring in one amino acid. If it fits, which it doesn't fit in this case, it will continue. It didn't fit, another one comes in. It now fits. And now things move, and the reaction takes place. Come on. Yeah. And now we've added one letter, and this keeps on happening. So this is the machine. I call it the inkjet, the 3D printer of the cell. Because it basically takes one-dimensional information and prints out something three-dimensional. This just shows the same thing in a detailed model. And this was made by simulation using complicated methods of morphing that just shows the RNA is the orange space-filling object that looks like that in the bottom left. And you see the tRNA is moving, and the molecule just moves by having a motion like this. Very simple. You could make a child's toy that does this, and the rope moves along, and things click. But biology is very clever. Okay. Then I'm going to say a little bit about applied computational biology. because all my life has been basic science. I was really interested in, until I got to Stanford. And I got to Stanford when I was, after about 20 years of research. I was about 40. And at Stanford, it was immediately saying, well, what startup company are you going to join? And I didn't really know. But they said it was a good thing to do. They'll have shares and you'll get rich and stuff like this. So I joined a company called Protein Design Lab, PDL. And this was a company that was trying to make proteins that would be useful. Protein Design Lab was founded in 1986, I think. I got to Stanford in 1987. And protein cloning was only available in 1986. That's the very, very beginning. And this was basically led to a pioneering therapy in cancer, something that I didn't really appreciate until much later. So essentially, antibodies work a bit like two hands with fingers that have different shapes. So the hands are fixed together, but the fingers are not moving. They have a shape like that. A different antibody might look like this. Another antibody might look like this. And this forms a cavity that in this case can grasp an apple, but antibodies can recognize millions of different things very precisely. And they do this by having a body and then loops. And there are 3 loops and a body, and there's 2 of these that come together. And essentially, in 1989, I wrote a key paper with the group at Protein Design Lab. And the title is very revealing. So firstly, antibody that binds interleukin-2 receptor. Interleukin-2 receptor is a receptor that is expressed, many copies of it, on the surface of cancer cells. So if you could recognize this receptor, you would recognize a cancer cell. Antibodies do that. What's the word humanize doing here? Well, the trouble is that the way you make antibodies is by taking cancer cells and injecting them into a mouse or rabbit. Then you extract the serum from a mouse, purify it, and find out what the antibody sequence is, and then you make the antibody in a lab. Trouble is, if you take that antibody and inject it into people, they get sick. So you have to humanize the antibody, and this is basically done by changing the fingers of the antibody. So the antibody looks like this, it has fingers, and Greg Winter from Cambridge proposed that you do this by just simply taking the fingers, shown here in red, from the mouse and the body from human. Queen, in this paper, had a better idea. They said, firstly, choose a body from human that is very, very similar to the body, the antibody here. And secondly, there's a region where the fingers touch that also needs to be changed. This led to a different patent than the Winter patent. It was very strongly protected in the patent. Big Pharma felt they were safe to use it to develop new methods. So human antibody therapies were started by the company Genentech, later acquired by Roche. It was very, very expensive. It cost hundreds of billions of dollars to learn how to make antibodies in the lab, to distribute them, to stop them going bad. The sad thing here, I guess, well, Protein Design Lab made a lot of money just from patent royalties. They were making something like $1 billion, $500 million a year in the last year before the patent expired. The patent started in 1989 and expired in 2014, 25 years later. But what is, I don't know if it's sad news or good news, some of these antibodies are still used today. One of the treatments for breast cancer is Herceptin. And it's off patent, which is good, but it's still a big deal. And we nowadays are hearing more and more and more about antibody drugs. Nowadays, there are clever ways of humanizing them. You can actually give a mouse a human immune system, and then the mouse makes human antibodies for you. Let me just mention 2 other applications. There's a company called In Silico Medicine, who since 2014 has been using generative AI to design drugs and to speed the whole process. Their method is basically to speed the drug pipeline. Drugs typically cost $1 or $2 billion to develop and take about 10 years. This is why nobody wants to develop new antibiotics. They'd much rather develop specialized drugs for old people that cost $1 million a year of use instead of widespread drugs. We have to basically find a way to make drug use cheaper. And basically, In Silico Medicine has found methods. They currently are a relatively small company, partially based in Shanghai, And they actually have 7 drugs in clinical trials, which is very impressive. And they essentially do it by using AI for all stages of the process. They also use AI for their clinical trials and for the drug design and for target discovery, because drug discovery is a pipeline. And it doesn't matter how fast you are, what really matters is the slowest step, not the fastest step. So you want to speed up everything, and they're very good at doing that. So they are able to do very, very fast things. Okay, so basically I want to mention a third company, which is actually using quantum mechanics for cancer therapy. This company is trying to improve MRI, magnetic imaging, so you'll be able to see physiological changes during the imaging. Now, the problem with MRI, many of us have had MRI scans, they give you great detail, so you can really see exactly what's going on, and you get the detail in 3 dimensions, but essentially you're seeing water. And because there's less water inside bone and more water inside water, and proteins have a different amount, you get contrast. You'd really like to see a metabolite in the thing, and you can't do that because metabolites are at a very, very low concentration. So say there's a metabolite like pyruvate. Pyruvate is a very simple molecule that is metabolized. If a cell is living, it will break pyruvate. So you need to basically make the pyruvate much more sensitively seen, and the way you do that is you can polarize the nuclear spins. Nuclei are spinning. You can make them all spin in the same direction. It's a very difficult process. Can be done by using very large magnets and 1 degree Kelvin, but you can also do it in the lab at low temperature, and this is what this company has done. They've made the whole thing very accessible, and it's really important because you now get a time case. The pyruvate decays, but before it's decayed, it can be metabolized. And once it's metabolized, the MRI signal changes. So you'll see whether the pyruvate is being used up inside the tumor or not. This is very important because if you have a brain tumor that you can't operate on, you give a certain medicine. You don't know whether the medicine is working until the tumor gets smaller. That might take a month. It might take 3 months. And normally if you have a brain tumor, your life expectancy is not very good. If you could see pyruvate not being metabolized in the tumor, you would say, okay, it's working, or still being metabolized. Okay, so a little bit about future of computational biology. It is definitely AI. I think the future of everything is AI. I have been using ChatGPT since the beginning of December 2020 and I think I've used it 10,000 times. I have for everything. It is amazing. So basically, I say a little bit about this. This is unnecessary. Basically, biology is very important in giving you the basic outline of using neural networks. Not really worth saying too much about this, but essentially, you try to find the weights of all those connections so the network starts to look like this and it's learned something. But this network is so tiny compared to the networks in something like GPT that it's a joke. This is 24 nodes. GPT probably has 1 billion, 10 billion, 100 billion, and so on. So these networks are colossal, very difficult to understand. There's a great YouTube by something called 3 Blue, 1 Brown. Amazing, really worth listening. But basically, essentially what these language models are doing is predicting the next word in a sentence. And for me, it's ununderstandable how smart they are by just predicting the next word. But it seems to be true. I mean, even the dumb ones are pretty smart. So essentially, one of the important things is to take a word and encode a word as a very high-dimensional vector. Typically, every word in all the languages becomes a vector in 10,000 dimensions. And the weights of the different dimensions are given by showing it lots and lots of text in many, many languages. Now, one property of high-dimensional spaces are that it's something called the curse of dimensionality, but actually it's a blessing. There are many, many different points in a high-dimensional space. If you imagine a space that's 100 by 100 by 100 in dimension 100, the number of points is 100 to the power of 100. That is much, much more than the number of electrons in the universe. So basically, a relatively small object, and imagine you have your space is not 100 by 100 by 100, but 10,000, you can store everything. And when you put words into the space, you start to see that meaning starts to make sense. So each word is a point in the space. And when you look at related words, so for example, man, the vector that takes you from man to woman is the same as the vector that takes you from nephew to niece, or maybe from cow to bull. So negativity, becoming female, is a direction. So meaning is encoded in the space. And essentially, they do this thousands of times. Every time you ask a question, there are millions of calculations done very correctly, probably billions of calculations done to get the next word and the next word and the next word. And out of this, in my opinion, comes something that, for me, is indistinguishable from intelligence. People say, I actually was telling Francesca that I see AI as being like a super smart, blind 10-year-old who has no experience in the real world, but super, super smart. And you have to act for it. Sometimes I actually feel that GPT is not working for me, I'm working for it. Okay. So just to say something now about AlphaFold, this is a computer program that could win the Nobel Prize tomorrow. We don't know. People are talking about it. But I should say, you could actually even argue that because people are talking about it, reduces the chances of getting it. The Nobel Committee hates to be predicted. The one predictable thing they did was for mRNA and vaccines, and they may still be sorry about that. Anyway, so AlphaFold is a computer program that was written before large language models by DeepMind, which is a subsidiary of Google. And they were able to do very well at predicting protein structure. Now, the reason they could do very well is that people had set up blind competitions to predict computer structure. And they in their first run, they were about double the second best. Now, it's important to realize that the amount of computing you have is very important, because if you predict, this is like the Olympic Games. If you have people in every category, you will win more. A big country will always win more medals than a small country. If you said the number of medals per country size, there would be a different win. But no one does that. They just simply say who got the most medals, and it is very difficult for a small country to get the most medals. In the same way, if you have limited computer resources, you cannot really compete with a big group. They did very, very well. They did better and better. But it's important to realize that the work they did was based on thousands of man-years of work. All the structures, plus methods. I mean, they really also needed to understand how to predict structure. And this was done using methods that had been developed in the past, and also having the basis for prediction. John Moult, who's a crystallographer, had decided early on that everyone knows how to predict a structure where you know the answer for. Predicting what you don't know is much harder, and therefore he got into connection with crystallographers and said, tell me what you're working on that you don't know the answer for, but in 3 months' time you will know the answer for. Give that structure to prediction, and that is a very good blind test. This actually helped AlphaFold because it could do blind tests. And their methods are very clever. They have very clever networks. They're using transformers very early on. Very quickly, artificial intelligence today, it's great for everything. Use it, use it, use it. I write code. I read contracts. I translate languages. I ask for emotional advice, legal advice, medical advice, everything possible. It's got high emotional intelligence. This is a paper that came out of Tsinghua. It was in the 90th percentile of people that they tested. I sort of joke and say they were probably all Tsinghua engineers and male, but I don't believe that. I think that if you ask GPT, if somebody comes to me and says, my girlfriend just left me, I said, don't tell me, ask GPT what to do. And no, but I'm not kidding with you. The advice will be really, really helpful. I'm arguing with my wife about taxis. You would not believe. And the great thing is if your mother gave you advice, you would say, she's trying to get me married, she wants me to do this. I don't believe her. But GPT's advice is very clean. It's not biased by anything. Another thing that I find amazing is that language models are really, really good at diplomacy. Now, we haven't actually tested them on real-life diplomacy, but there's a board game called Diplomacy that was very popular in the 60s. And I remember my uncle and aunt, whose television I watched, were big diplomacy players. But a paper came out of Facebook from Meta, where they wrote a computer program called Cicero that is the world champion in diplomacy. Now, where diplomacy works is you Shuffle, and you're given parts of Europe in 1901, different parts of countries. And the idea is to swap pieces until you control all of Europe. So understanding the different values of different parts of the board is incredibly valuable. And GPT, or AI, is really, really good at this. And the people who lose to AI are actually not unhappy at all. They're actually really, really happy because it doesn't cheat, it doesn't stab anybody in the back, it wins by just knowing the situation better. So let me just end with a few general thoughts. And I'm ending slightly earlier because I love discussion and questions more than talking. So my technology has been driven ahead by technology. My work has been driven ahead by technology. And I was actually asked this question about a week after hearing about the Nobel Prize. And for that first week, you're just being asked silly questions, like what does it feel like, and so on. And this, I thought, was an interesting question. You know, how much have computers changed between 1967 and 2007? So I actually did the calculation. And what was interesting was that the cost had come down by about 10,000 times. The speed had gone up by about 10,000 times. The memory had gone up by about 10,000 times. And the size had gone down by about 10,000 times. Now, these numbers are from 1967 to 2013. If we looked at this today, you'd definitely add some zeros at the bottom there. So then, actually, use a slide, not slide, but a talk when I gave my Nobel dinner speech. But basically, you can now say that if cars were like computers, then a new Volvo would cost $3, would have a top speed of 2,000 kilometers an hour, would carry 50,000 adults in comfort, and would park in a shoebox. Now, that's true. I mean, if computers were, but this is really interesting. And it really means that we've had this, and all of those things actually matter. If I had used, maybe instead of size, electrical consumption, things that have increased by 10 to the 12. This is a big, big, big number. Plus, you know, every one of us carries in our pockets something much, much faster than the computers that were available even in 1980. So things have really, really changed in a way that's very, very dramatic. There's the same thing in Chinese, but I think it's unnecessary. So I just want to end with my advice to the young. Be passionate. Do something you like doing. It's really hard to predict what is the next big thing. I actually think it's impossible to predict it. Every person who's tried to predict what we should work on or shouldn't work on has been wrong. So do something you actually enjoy doing. Often I give the example, if you're a student and your parents really want you to become a doctor, you actually would prefer to be a pianist, and you become a doctor, and you're a successful doctor, you now spend your whole life doing something that you don't really like. That isn't a good idea. The other thing is, be persistent. Don't give up. You know, every new idea is going to be rejected. That's the way things are. And so therefore, be persistent. Be creative, be original. If you do something that somebody else has said, you're behind. They had the idea first. And as part of being creative, I would say two things. Very often when you take disciplines that are very different and put them together, if two people in different disciplines can even talk together, they will have an idea that could be earth-changing. Because at the edge of disciplines, there are major interests, and just being able to talk could lead to something different. The other thing is, in life, be very open to new things. Be early adapters. Never say, oh, I don't really want to use a cell phone. Never say, oh, I read books on paper. Who wants to read them? People, you know, I use a typewriter. All of these things are not good things to say because you're going to be left behind. And often they're said by people who don't actually try the new thing. And I think it's really worth trying new things, being an early adapter as much as you can. And finally, be kind and good. I think that in life, it really helps to be kind and good. There are some scientists who try to beat their neighbors, beat their competitors by not referring to them, by putting them down, by changing history. That's a very bad idea. In fact, I think not referring to people, you cannot tell how you win a Nobel Prize, but you can almost certainly not win a Nobel Prize by doing Nobel Prize-winning work that doesn't refer to earlier work. So with that, I want to thank you all for your attention.
Thank you very much, Professor Michael Levitt. And please remain in your seat, and we will have another session, a dialogue session, to interact with Professor Michael Levitt. So this dialogue session will be chaired by Dr. Francesco and also Dr. Yongshen. Let us welcome.
Hello? Okay.
Thank you.
So we have a session for questions and for discussion. And I hope students want to ask questions because at the end this event is for you mainly. But just to warm up, I leave Yongshen to warm the public with the first question. Do you have anything that you want to comment or something that you want to say?
Thanks, Francisco. And my name is Yong, and I'm the assistant professor for School of Science and also the program director for the undergraduate biological science program. And so a very great and inspiring talk by Professor Levitt. And so I think the first question I would like to ask is that, so back to 50 years, like 1967 something. And I mean, the time, I mean, before Steve Jobs, before Apple, before Bill Gates, and even before IBM, and how, I mean, what motivated you to use computation methods, right? Algorithm to decode the biological problems. That is way ahead of the time, right? Yeah.
So that's a great question. I remember when I was about, maybe 1961, 62, I heard about a large computer that could play the game of tic-tac-toe, where you have 9 squares and you have to put a 0 on X, probably a very ancient game. It's very easy to draw or win. But I heard a computer could play it, and I thought, my God, computers can't just add and multiply numbers, they can play games. And I suddenly said, I want to work with computers. When I was 16, I think, I went to a computer class in London with a company called Elliott. They don't exist anymore. The programs were all on paper tape. And I started to love computers, and I think in some ways, if I was alive now, I would probably become somebody working in hacking or something like that. If I was young now, I just loved computers. now you don't have to have anything special. You have computers around you. So in some ways, I feel incredibly lucky that I could keep on using computers. Also, I like to do things myself. If I have students, they write programs, I write programs. It's not that I have people working for me. And it's been very lucky because it means that I can still enjoy writing programs now with GPT because I do it myself. So I think it was just a lot of luck. But you know, many things were pure luck. I didn't want to go to Xi'an in Israel. You know, I'd much rather have gone to Boston or Tokyo or some more exotic place. I didn't know him. So life, but I was smart enough not to disagree completely. So I think you should be persistent, but when opportunities come, take them.
Thanks. So if you have some questions, you can hands up, and we can give you.
There are some microphones. Okay. So in the meantime, speaking of computer, this is a very philosophical question, if you want. But we are used to understand things with science. So how humans understand things is simplifying what they see and find out rules. Physics is the most probably powerful science because it's simple enough. But when you get to biology, the concept, the interaction are so complicated that you need to use simple models to get some understanding. But now artificial intelligence especially, is giving us a new way to understand, to see the world that we really don't understand. So I think neural networks are changing the way in which we can interact with reality, with our experience. And I'm not sure we can comprehend this until the end. What do you think about this?
So I think, you're right. I think there have been things we could do on the computer, even much simpler things like simulation. One of the big problems in physical chemistry over the years has been the structure of water, the structure and the dynamics of water. And basically in 1969, almost 60 years ago, Raman and Sillinger simulated water movement in a box, molecular dynamics, the very first use of molecular dynamics on water. And this gave pretty good results. And suddenly all the questions about the structure of water disappeared. Now, nobody understands, what people now say is if you take a simple water molecule, put it into a box and let it move around, it acts like water. Is that understanding? I don't think so. So I think we have a problem. I think the problem is going to be much more difficult. I've thought a lot about AI in general, overtaking human intelligence and so on. I don't see it happening because I'm a great believer in diversity. I have several other lectures all emphasizing biological diversity and other diversity. And it's absolutely clear to me that no matter how smart computers are and how smart people are, together they're going to be smarter. A plus epsilon is greater than A. And therefore, there'll always be an element. I think what we mean by understanding, you could also argue that AlphaFold is a little bit disappointing because nobody's been able to say, we now understand why proteins fold. There are people, mostly publishing in Twitter, that have shown some very strange things about AlphaFold. You can take a sequence of a protein and make half the amino acids lysine, and it still gets predicted to have the same structure. And this is physically completely wrong. So I think very often these models work in a limited domain, sort of a valley of likelihood, sometimes called the uncanny valley. And I think that we will learn, but I actually think the future is going to be a combination. I really am, I've spent so much time with all the variants of ChatGPT, and I think I've learned how to get the best out of it, but it's not simple. It really is like dealing with a prodigy who's very smart.
Yeah. Have you watched the movie Matrix? 黑客帝国. Yeah.
I have watched Matrix, and I've watched Her, and I've read, although my favorite book is Xi'an Jiaotong.
If you believe that the world is by data and computational, at least they use a computational way to understand the world.
One of the big problems with understanding the world by computation is chaos. And you can do calculations to 1,000 different places and still not get things to exact. And I think that nature is very precise. Biology is able to make the same protein. It makes mistakes, but even though that we're operating at room temperature, high energy, we get things right. So I think there are solutions, but the solutions may be more clever. I think we have a lot still to learn from biology. If you think about the amount of energy required to solve a mathematical equation yourself or by AI, there's no comparison. So I think it's going to be a learning experience. I actually think we don't know. What I do think is that anybody, I see AI a bit like the smartphone. One thing about the smartphone is about 80% of the world has some kind of access to a smartphone. 80% of the world doesn't sleep in a bed, don't have breakfast every day. I mean, 80% is a very big fraction if we include all the people in less developed countries and Africa and so on. But there will be one smartphone per village, one smartphone per community. And smartphones are going to get much, much smarter. And there's no doubt that if you took anybody and took their phone away from them, they would become less smart. So basically, having a smarter phone will make us all smarter, and I think we'll be much better equipped to deal with the future. For me, this is what gives me a lot of optimism. I also believe that one of the good things about AI, I was joking about the game diplomacy, but one of the things about AI, if you're a very powerful person, the head of Google, and you want to ask somebody, well, is this idea any good? You can't really ask your secretary, you can't ask your assistant, because you'll be showing weakness. But you can ask AI. And I think there will be very interesting questions that you can ask AI, and I'm sure leaders will start to get a second opinion or a third opinion. And I think this will lead to much, much more carefully considered decisions. So I think we can look forward to a much, much better future because we'll all be smarter. And as we've become smarter, thanks to, we haven't become biologically smarter, we've become culturally smarter, thanks to speaking, writing, books, internet, AI, just a progression of more and more information, more and more help. The world has gotten better. However bad we think the world is now, it was way worse 500 years ago and 100 years ago and so on. There are ups and downs, but still the average is improving incredibly much better. If you look at life expectancy, children who are dying in birth, women versus men, things are much, much better. And I think this is due to the fact that we're becoming culturally more intelligent, and AI is going to lead to a big, big jump in cultural intelligence. So I think reason for optimism.
We have a question from one of our students.
Hello, Professor Levitt. It's an honor to be able to ask you a question. I'm a student, Amer, in international business. And I'm asking this question because I had a concern about the current direction of the evolution of language learning models, because I feel like at the moment we're increasing the computers and the computation power, but we're not really focusing at the algorithm and making it more efficient. And with the current pace it's going, I feel like it's just going to continually increase the computation power with more costs and more electrical usage, but not really focusing at making the algorithm itself more efficient, because most people just want quick improvements.
Can you repeat the question for me? My hearing is not great.
Yeah, could you repeat the questions?
Yeah.
So, yeah.
I think, the key thing is not faster, it's less energy. And I think that we are improving algorithms. What I think is going to make a huge, huge difference is using energy efficient chips. I actually believe that all the old-fashioned chips, like those used by NVIDIA or Intel, are going to disappear. And the really important chips are going to be the chips like the ARM chip used by many cell phones or Huawei's chip. Because the key thing in AI is how much energy per multiply. And these old-fashioned chips are just, you can make them go faster by more and more heat, but it's not the solution. So I think there will be massive improvements in algorithms. Basically, we're all going to be smarter. So we're going to improve everything. It's not just the speed. Speed is the first thing we improve. We had to get the speed. And it's also interesting to ask, how come computers got so fast? And it's got nothing to do with the good reasons. It's for two bad reasons. One is, for Intel chips, Microsoft got slower and slower every version of the program, so you had to have better hardware to keep the word processing the same speed. Another reason is that teenage boys like to play games, and because they were playing games, they led to the development of the GPUs that have basically led to the development of AI. So in some ways, the heroes of the whole story are the delinquent 14-year-olds playing games. Don't forget that.
Thank you so much.
Yep. I see it over there.
Must be another microphone. You can leave it there, Francesco. We can share. Leave it there.
Dr. Levitt, okay, I enjoy your talk, okay. I'd like to ask you a big question. My question or questions are related to a recent event that affected, everybody's life. I'm talking about the COVID pandemic. Okay, during the pandemic, you and your colleagues did some work, right? Including, okay, I'm sure you used computational modeling, made some conclusions and predictions, some of which turned out not to be true. But my question is not about that. My question is, will there be another pandemic? Okay, if it does come, how should we deal with it? Can we, as scientists, can do something about it? Okay, because a lot of people are very concerned about the possibility of another pandemic in the not so distant future. Yeah, I'd like to hear your opinions. Thank you.
Thank you for that question. If I had to pay for a question, I would really pay a lot for that question. So thank you so much. So basically, let me say the following. The pandemic was very interesting because it was real-time science. So normally when you do science, you get a result, you have time to check it. But in COVID, there was no time because you wanted to get the results very quickly. And the big questions about COVID were, how bad is it going to be? And how is it spreading? And together with Professor Zonta, I did work on both of these topics. We were collaborating all along. And without actually getting into details, I think it's interesting in your terms about other pandemics. So basically, there have been many, many pandemics through history. Usually not COVID pandemics, because there were much, much worse viruses and bacteria. The bacteria, Yersinia pestis, the Black Death, was killing something like 10% to 50% of the population. COVID, in the end, killed about 0.1% of the people who got sick. Natural death is 1% a year. So it's less, but if the death is 10 times more than natural death, you really feel it at 10%. I remember writing an article. I was asked by, I think, the Wall Street Journal, but I forget now, to write an op-ed about COVID in March 2020. And I wrote an op-ed, and in the end, they didn't actually accept my op-ed, because I didn't say bad things about China. I was talking about, and they were very anti-China. But my last sentence of the op-ed was very interesting. I said, and this is very early, I said, I am not impressed by how humanity has dealt with this pandemic. This is March 2020, so it's very, very early. But I'm optimistic because by the time there's the next pandemic, computers will have advanced sufficiently for us to simply say, hey Siri, Alexa, Google, should I panic and believe the result? Now, basically AI is getting to that point, and the model I use is, my phone wants me to talk to it. Basically, if you think about driving, 15 years ago, you had to be really smart to find the best way to drive around Shanghai. Taxi drivers were skilled. And then we started to have GPS and GPS programs. And at the beginning, the smart driver said, I don't need to use GPS. I know the right way. This GPS doesn't work. But nowadays, hardly anyone will go against what all the maps say about driving. So we trust driving. We've learned to believe, and this was oftentimes in a car, the wife would say, go the usual way. The husband would say, no, 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 I want to go a new way. And this led to divorces, I'm sure. So basically, this was a very important tool for that. Now, we get used to getting good advice from AI. You know, should the children be sent to school today? Or stuff that we care about. What should I wear when my wife is wearing this? What should we cook for our friends? You'll start to believe it. And unfortunately, risk assessment. People are not very good at finding the best route through a traffic jam. The Dijkstra algorithm is very good at doing it. It does exhaustive enumeration, and it has real-time data. In the same way, people are very bad at assessing risk. We don't understand, and this is one of the big problems. You know, one of the first things I did in COVID was to ask how many people die every day in the world. and it's 160,000 people die every day in the world. So talking about 1 million deaths might sound like a big number, but it's only 5 days of normal death in the world. The other thing about death is to realize that, unfortunately, when you're older, you have more chance of dying than when you're younger. That's probably a good thing, because we care about young people. So I think that we're very bad at assessing risks, and I think AI is very, very good at assessing risks, because it can evaluate all the data in an unbiased way. So I actually think that there will be future pandemics. I should say another thing. There is still a lot of antagonism to scientific work in COVID. And I've decided that I'm no longer writing for people. I'm writing for GPT. My papers will be out there, they will be read, and when there's a next pandemic, it'll assess those papers like all other papers, and there'll be answers, there'll be solutions. The other thing about COVID is everyone said it's a new virus, but common colds, 4 of the common cold variants are COVID. The other 4 are rhino. So we've had COVID virus, and if you look at history, people talk about the plagues, the pandemics. They were never COVID. They were always something much worse. Flu is probably a worse virus than COVID. It's a very nasty virus by its biology. So I think that we can learn a lot. I hope that our getting smarter will really improve things. The pandemic, unfortunately, had a lot of bad consequences. The global deficit of the world increased by $40 trillion. That's a lot of money. The US deficit increased by $7 trillion. With that money, you probably could have solved electric vehicles for everybody, easily. I mean, $7 trillion is a lot of money. So unfortunately, not thinking carefully enough was a bad idea. For me, it was very exciting. There's nothing like real-time science. And even a lot of antagonism was fine. One thing about a scientist is you usually don't care if somebody says you're wrong. Because if you do something that's new, they will always say you're wrong. That's the nature of science. I mean, science is conservative. And basically in science, everything is wrong until there's evidence to prove it right. So you shouldn't be upset about people saying what you're doing is wrong. Just believe it. Anyway, thank you for the question.
Right. And I really believe that the technologies really help humans. I mean, suppose 100 years we have a great cold, and we have no technology to deal with it. But for this COVID pandemic, we have a sequencing technology, so we know the virus sequence after 10 days once we know the virus. So I think probably the AI computational technology also help us to prepare the next pandemic, which is Professor Levitt's great work. And so questions?
Okay, here is a question.
Thank you very much, Professor Levitt, for the talk. I have a question about the force field, actually. I think you are the expert of this kind of stuff. So as a development of the machine learning, so there is an emergent trend for the machine learning force field to replace the ab initio calculations, right? And now I'm just curious, how much do you believe these kind of first principle simulations can predict the material properties of large-scale condensed phase systems? How much do you believe this kind of compared to the experimental assessment or measurement?
A part of my work that I didn't talk about that's going on is actually to make better force fields using quantum mechanics. And this work, it turned out, was very hard to be funded by national funding sources in America, because basically too many people believed in the classical force fields that we had started 60 years ago. And they thought this is the best thing you can ever have. And in determining these quantum mechanical force fields, there's tricks you can do, many, many tricks. But what we're now doing is to use a force field as like a background, and for special cases, using machine learning. So I think you can combine machine learning almost as a perturbation on a force field. I think machine learning by itself will be fine for one particular case, but so for example, if you think about protein structure, protein structure, there's not very many different kinds of atoms. But if you think about the space of drugs, the number of different drug molecules is massive, or the space of molecules for organic lasers, or the space of molecules for organic chemistry. It's a very, very huge space, and nature chose the amino acids very carefully. When we look at proteins, nature spent a lot of billions of years choosing the right chemistry. But if we want to make new chemistries, we can't rely on that. And when the chemistry changes, it's very hard to have enough previous data to get that thing. Chemistry is full of exceptions, full of very special interactions. So I think ultimately the best approach is going to be combining quantum mechanics, quantum mechanical force fields, and AI. And I always believe, I believe very much, people tell me, what country do you like best? And I tell them, I never choose. I like A and B and C and D. You don't have to choose. You can combine. And that's also a secret of biology. You have genes inside you that previously were inside all sorts of organisms. We didn't kill those organisms off. We just took their genes. So basically, combining is a very good policy.
Okay.
Any other questions?
Here we have a question from a student.
He has waited for from a lady, maybe.
Yeah. May I have a question about your Nobel Prize? And it is a little academic. Wait a minute.
Where is it?
That is, I know quantum mechanics can compute atomic or molecule orbital to predict the reactions, just like Hohmann and Lumo, right? And it is effective, I know. But the problem is that those biological macromolecules are too large, and I think the little energy changing in it is too small. And there is another effect different from or hydrogen bond or pi effect. It is called hydrophobic effect, and it is based on Gibbs free energy. And I want to ask, how can you deal with the quantum mechanics and the thermodynamics to compute, or your work is just based on one protein? If there are two proteins, they are reacting, and I think they are so large, and the thermodynamics will be more well. Thank you.
I wish I could say I understood what you said, but I don't. And I don't. Did any young ears understand that? Please.
This question is about your Nobel Prize.
Okay, so I'm going to assume that your question was, proteins are very big, how can we worry about the details? And, computers are very good at details. But I'm sorry, maybe you should come forward, and maybe if I see you, I'll be able to understand what you're saying. Or maybe somebody can understand. I'm really sorry, you're under the lights, so I can't even see you.
你要到前面，可以过来。你可以到台前来，然后问问题。
Or even Chinese, and someone will translate.
要不然，你用中文跟我说，我来翻译。有些学术单词，没事，你说我听得懂。就是说，用。要不然之后再讲，现在。Professor Levitt, he is going to communicate with you later on. It will be fine. Yeah.
Fine, if this time.
Okay, Professor. I'm a stage 1 student who want to study biology. And there is a strong correlation between mathematics, physics, chemistry, and biology and computer science. I want to know if a biologist study physics or chemistry more, does he lose the original meaning of biology? Or it's a progress of the biology? So in your opinion, what's the true meaning of biology? That's my question.
You know, I see biology as very simply looking at the intelligence that biology has used. Biology is really good at making thinking machines. Biology is really good at making moving machines. We can learn from biology. So for me, I see biology as a form of intelligence. Biology has solved many, many problems in the real world. It's done it by evolution and many, many billions of years of debugging, but it has very, very good solutions. Look at a hand. Robots could make my hands, but they copy people. Even now, AI is copying a neural network from our brains. So I think biology, the important thing about biology is it's created all this wonder, and I'm not being religious, I don't care whether it was done by God or by randomness, but it wasn't done by us. When you look at protein molecule, we didn't think of a protein molecule. If you were in manufacturing, imagine you could make a car by just writing out strings of rope, and it would tie itself into knots by itself, it would self-assemble and create the car. Biology is really clever in assembly. It's really clever in energy use. It's really clever in so many things, and I think every field should be learning from biology. I think there are so many ways in which biology is doing clever things, often very difficult. But it's like an alien intelligence that has created all the life around us. Now, when you talk about different fields, I think the distinction in fields is just historical. It makes no sense. If you like, the one field that I never studied was chemistry. Getting a Nobel Prize in chemistry has zero to do with that. But you know, the molecules I think about are chemical molecules. But the chairs you sit on are also chemical objects. I think that we need to get rid of disciplines. They're convenient because you have departments and you have deans and you have things like this. And teaching is a problem. But I actually think that teaching is going to be changed completely by AI.
So you think biology is actually a natural AI?
Biology is a natural AI.
Yes, biology is definitely a natural AI, but it's complementary. I mean, AI, you know, AI just makes many things easy. So if you wanted to have a class where every student has its own teacher,
Okay.
you can do that with AI.
Okay.
Or
I want to ask a question more. Is that your achievement? You think is something that will happen soon, or
Yeah,
you think it
the
depends?
question is application for Professor Levitt's finding something?
No, I think your achievement is depend on luck, or is something that depends on your knowledge, or it will happen definitely.
I think
basically,
chance
Michael,
is-
she was
chance
asking
is-
whether or not you believe your achievement was based on luck or your hard work and knowledge.
I believe luck is really important. You know, as I said, I would say luck is very important, but basically, when luck comes your way, go with the luck. You know, I think that sometimes if I had planned out my life when I was 20 and said I want to do this, this, and this, and I stuck with that plan, I would have been much, much, much less successful. So basically, many things happened. For example, during my PhD, which I finished quite young, we had 2 children. So when I was working, there was always a baby around. Now, you might say that's bad luck, but it was actually very good luck because I couldn't work too hard. No, and one of the biggest dangers is working too hard. Because when you work too hard, you become stupid and you start to hate your work. I'm not kidding with you. So I think that, you know, and I mean, I was involved in, when I wasn't working on the computer, I was hand washing diapers. And it was a good way of doing other things. So I think that, you know, things are not, life is much less direct than we think. And things happening by chance can be very, very powerful. Now, there's also bad luck. I mean, a lot of people have bad luck. And if you like, the worst luck that you can have is to be born and live for one day. And it happens to people. But I think you need to really think that, feel very lucky and embrace change. You know, one thing, when I was maybe in my 50s, I didn't like change. I liked to write papers on longhand and things like that, or I didn't like to read books on the computer. And then suddenly I decided, this is crazy. I should be adopting everything quickly. Cell phone quickly, AI quickly, and even if it's difficult, it becomes easier. The way you go from an old thing to a new thing becomes easier with time, and you become quicker. And it's full of wonder. And you know, I also, it's just more interesting. So I think that, you know, in life, so one thing that was said to me by Francis Crick, who's probably the smartest person I ever met. He said something which I was surprised about. He said, when you're working in life, you should never be more than 70% busy. So you always have 30% spare to work on something new. And that's a very good thing. It doesn't make sense. You know, you're working, it's like never drive your car very fast. And this is like saying always, you know, don't go too hard. Very unexpected.
Hi. Professor Levitt, that was a very inspiring talk. Thank you very much for gracing our university. My name is Yoromi. I'm very impressed by the last slide that you gave to our young children as advice, where you said, be passionate, be persistent, be creative, and most of all, be kind and good. With AI, I'm confident that we can teach AI to be kind and good. What do you think? Whether 80% of our humanity could learn to be kind and good?
I think, you know, people who are not kind and good often have very hard lives. You could imagine if you grew up hungry and your parents left you, or you were beat up by somebody. I mean, bad things happen to people. And I think those people have every reason. You know, life isn't fair. I mean, unfortunately, life is not fair. Some people have good luck, and some people have bad luck. In exactly the same way, when I speak, some of these heated molecules will hit the wall, and some will come first, and some will come last. Everything has a distribution. I mean, life is full of distributions. And I feel very sorry for people who don't have this. But I think that, firstly, one should always think that everything you have is by luck. And the reason you should think that is that you didn't deserve it, you're lucky, so give it back. I think giving things back is very important. You know, I have lots of crazy ideas. And one of my crazy ideas was to imagine, this was maybe 10 years ago, and now it's possible, imagine everything is controlled by computer. The computer knows everything and whatever. But you're not really controlled, but the computer knows what we're doing. We're living normally, but so the computer knows when you have bad luck. You get a disease. The computer could then say, suddenly you win a lottery. So your chances of, everyone has a random chance of winning. Let's just say it's money. And nature is set up in such a way that when things are bad for you, you're poor. Your son dies unexpectedly. Your parent dies unexpectedly. Suddenly, a bunch of money lands in your account. And you could use this. And on the other hand, if you're having great luck and you're making trillions of dollars, suddenly money disappears from your account. And this would be a very good way of balancing things, because I think that there's no easy way to balance people. There's actually a movie that was made based on a book by Kurt Vonnegut called Garrison somebody, I forget another name. And this was a book of a future after a nuclear war, where they said that wars came because people were unequal. So in this book, what they did is they made everyone stupid. And if you were a very good dancer, they broke your legs, and so on. Now, that is not a very good way, but it was a way to avoid wars. I would much rather have randomness improve the life of people. So basically, you can change luck. I mean, if we're all connected to the computer in some way, your bank account can go up and down based on other things. And it's a great way to avoid poverty, have more equality, but still have individuality. I don't know what the solution is going to be, but I think AI will change things in the future. Governance will change, societies will change. This is where the big changes are going to be. The changes in science are going to be quite small. But I think we're going to have massive changes in human relationships and things like that because of understanding better.
Hi, Professor. I'm a stage 1 student, and I want to ask you about 2 questions. The first one is about AI, and the second one is probably about science. So you just said that like AI is like super smart people that you can ask him whenever you want. But like in my opinion, AI is generated and it's based on the informations on internet. So I would like to ask, for example, so in my opinion, AI is more like a dictionary that you can find something on it. So I want to ask if I have an open question that do not have an existing answer, and when I asking, for example, a very smart person, for example, a great scientist like you, and I ask the same question to AI and I get like 2 different answers. So which one should I be more respected, or in which content should I to generate them? And the second question.
Let's do the first one first, I remember.
Yeah, thanks.
So I think that, any answer you get from anybody, no matter how smart you think they are, should be thought about very carefully. You should have your own answer that is based on a synthesis of different answers. What I have found for myself is that AI, for example, is not very good at mathematics. Maybe it's getting better, but it's not great. There are websites out there that can simplify complicated expressions in algebra better than AI can. But that's good. The other thing is it's very bad at searching. If I ask it to search the web, I can do better than AI for searching. So, I don't mind that. I do the searching, it does the other things. It's great for writing code. It's great for even discussing concepts. You say, I'm planning to write a paper about this. Even before you do anything, can you find a fault in my approach? So powerful. Because when you start something, you don't want to hear about faults. You just want to write. Or else you can say, I did this work, other people have done this work, is my work still valuable? So I think, I think it adds a dimension. It isn't the answer to everything. And it's not like I'm not going to doctors because I use AI. But remember, it's very accessible. It doesn't cost very much. It's a second opinion. It's very easy to ask. But if I said I believe everything that AI says, I can also get different answers. I remember what really made me like AI very much is in December 2022, people were still very angry with me about COVID. And if you went to the web and you said Michael Levitt COVID, you would just find bad things. So when GPT 3.5 came out, the first thing I said is, tell me about Michael Levitt and COVID. And in those days, you could say, give me another answer, tell me again. And I actually got 20 different answers, and I kept them all. And some were really nice. One gave me 2 Nobel Prizes. One took my Nobel Prize away. But it was actually just very nice to get all that opinion. So basically, now, being narcissistic, I liked AI because of that. But the fact is it was a way of getting a feeling. It also made me realize that a lot of the information, if you took all the information on the internet, when I was searching for myself, I was looking for the bad stuff, whereas GPT was being more balanced. So I think, you have to use it, and I would say the following, it isn't easy to use. In the same way, when the smartphone came out, most people couldn't really use it well. And every one of us can remember when people told you how to move the cursor backwards, or how to make a screen capture, or how, people didn't understand how to do this. AI is very, very complicated. And we want as many people to play with it and to tell people. I'll give you an example. About a year ago, GPT started to understand voices. We were actually in a restaurant with an Italian friend, not Francesco, and I said to him, just say something to AI, it will understand your Italian. And he said something, and AI translated it very nicely, and then said, oh, your friend said something very nice about you. Then I discovered, in any language, people can talk Chinese, it will understand every word you say. So the problem of going from speech to writing was totally solved by OpenAI, completely. More than iFlyTech, more than any other company, more than Siri, more than Google, more than Alexa. This company completely solved the problem of talking in maybe 100 different languages and getting the text. That's a big deal. If you've ever been to a conference when they have simultaneous translation, it can't understand the English. If you speak English with a foreign accent, GPT will understand you, but most programs won't. So that's a big advance. No one even talked about that advance. It just turned out that it was just accepted. So I think that these are massive, massive changes. As a result of this, I believe that my phone will be speaking perfect Chinese in 3 years' time. Perfectly. Now, I probably won't speak Shanghainese, but it'll certainly speak Mandarin and Cantonese. So we're going to have this massive revolution. And these developments came without even expecting them. Things are changing very, very quickly. And you have to play with it all the time to catch the changes. So my advice is, and it doesn't really matter which AI it is. I just happen to, this one was the first, and I use it a lot. But this is a more difficult one to use, via VPN and stuff like that. But there are many other, and again, it's like a friend. You have to talk to it a lot to know where to get the best from it. But you don't believe, if your friend tells you something and you always believe them, then you're stupid. You don't believe your friend always. Sometimes yes, sometimes no. You want to answer your second question?
Yeah, so like I'm a stage 1 student, and you said that you first learned some like basic science, and like in your afterlife, when you are working, and you are working on some like technologies, like solving problems. So I would like to ask, how does the learning of basic science help you while you are solving problems in real lives?
So, some people have said that there's no such thing as basic science. It's just a question of how long it takes to become applied. And you could probably argue that if royalties were paid not just for 25 years, but for 300 years, then the richest person in the world would not be Elon Musk, it would be Euler. Because Euler understood how to factorize large numbers. And this mathematical trick of factorizing large numbers is worth trillions of dollars because every bank, every WeChat, every Alipay uses it as a code. So that's the most applied science in the world, but it started out as pure number theory. So I think it is, if you could tell me something basic that will never be applied, I won't believe you. But I think they go together. I think the big difference between basic science and applied science is the following. When you do basic science, you generally don't care about what you did, you care about what you will do. And somebody should be, I remember when I was in Cambridge as a student, everybody was as good, not as their last paper, but as their next paper. And that's a very tough rule. I have my last 10 papers are all in Nature, I have no new ideas, bad. Now, in applied science, it's exactly the opposite. In applied science, you want to make as much money as you can from your old idea, so you will still be in business to use your new ideas. It's the same thing, but with a very different focus. And when I first started to work with Protein Design Lab on antibody design, I had written papers about antibodies. I thought it was boring. I just had to write a computer program that would help them. It wasn't interesting. I didn't realize the commercial value or the medical health value, leave out the money. I mean, so many people today are alive because of a drug like Herceptin. So, the different value system. Essentially, in basic science, it's I got the idea first, or I made it better. Applied science is often making it better. I think making it better is also very important. Very important. Manufacturing cheaply and well is incredibly important for the world. If people had not copied the iPhone, there would be not 80% of the world, but 5% of the world, and they would be still costing very high prices, and we would all be suffering. So I think that all of these things work together. I think, what I see happening, one of the really nice things about AI is to learn quickly about a new field. Say I'm interested in ancient Chinese astronomy. I can actually have a conversation with AI about this, and then say, I still don't understand what you mean. Please, I understand Newton. Can you now make a connection? And I'm sure very quickly I would understand amazing things because it's read all the literature. So everyone might say it's everything on the literature, but for me to go and read ancient Chinese astronomy is very, very hard. It's even hard for me to read, some certain encyclopedias. So it's very good for that. It's very easy. If you're in biology and you want to now do something in computer programming, you can do it without ever learning computer programming. You can write computer programs now today without knowing. Now all my programs are in Python. It's a language that I hate and I cannot write. And I hate it because it's a very big language. You have a language like C, there's maybe 100 commands you have to remember, and that's the end. You can do anything. But in Python, there's 10,000 libraries you have to remember. It's very powerful for that reason. So without AI, I would never use it, but I can use it. So I think it's very good for learning new things, even other things. If I wanted to learn about antique motor cars, or antique watches, I want to start to collect old watches. I'm sure I would become an expert very, very quickly by just through AI.
Okay, due to the time limit, we only have room for one question. We don't want to keep Professor Michael Levitt being too exhausted.
We gave it to some girl, right?
Maybe a woman.
There.
We reserved one.
Hello, Professor Levitt. I'm currently a second-year student, major in biological science, and I've looked at, I've go through your autobiography you uploaded in Nobelprize.org after you won a Nobel Prize, and then it mainly introduced your research life as a from Cambridge to Weizmann Institute and back to Cambridge and back to Weizmann Institute again, and then end up as Stanford. And however, as a undergraduate student, and I'm a little curious about how did you your undergraduate studies, like in South Africa and in KCL, contribute to your following researches, and what the qualities and knowledges you gained in your undergraduate studies to contribute to your future researches? Yeah.
I'm sure my undergraduate studies contributed enormously. I think you learn from everything around you. It was good to learn applied mathematics. It was good to hear. In fact, I heard about some of the early work on protein folding in a lecture in my third year at King's College. There was work by somebody called Harold Sharaga, who was doing very early work not on protein folding, but on folding of small peptides. So I think, everything you hear influences you. I think the most important thing in life is to be open to new ideas and keep on learning. And you can learn from everybody, and you can learn from anything, and it will be unique. So I don't think there's any special single source for this information. Just remain interesting and embrace things, try new things, and don't work too hard.
So before closing and before all our studies shift to computer science, can you say something about yesterday Nobel Prize for microRNA? Just 2 words.
I didn't really learn too much about it. Yesterday I studied it. I think microRNA is an example of how clever nature is. So basically RNA is normally used as a messenger RNA. But this is like in the old days when I was at school, people would send messages on paper from one to the other. And these messages were very short, full of abbreviations. So if you like, microRNA is like the school messages, and these messages you didn't want anyone to see them, you would hide them. I'm sure now you send a text maybe. But back in those days, there were very short messages with abbreviations. And it would be, I love you would be I, whatever, some very short. Like there were no icons in those days, no emoji. I think these microRNA is a way to get communication that controls the way cells work. And nature is very opportunist. Nature will try everything it can. So I think maybe what happened, the early thinkers, certainly at the time of Watson and Crick and later on proteins and the pioneers, they didn't think about microRNA. It seemed unnecessary. But basically, I think it's just an example of how clever biology is. And it's great that it will be useful. You know, people might have said, well, don't work on short RNAs, they can't be useful. And that's a stupid statement, and I'm sure somebody said that. Many stupid things. You know, never say don't. Embrace, have multiple things. Never say A or B, say A and B, so on.
Well, I think that brings us to a conclusion. But before we bring this officially to an end, I'd like to, on behalf of our president, Professor Vivian K, and our provost, Professor Xi'an Jiaotong-Liverpool, who would like to present this award to you, Michael. Thank you so much for attending the event. We deeply appreciate it. We look forward to having a repeat event this time next year, hopefully with another Nobel Prize winner. Maybe Michael can recommend one. And I want to acknowledge one more person. Actually, Michael's presentation today was possible because of his close friendship and appreciation for our own faculty member here, Dr. Francesco Zonta. So many thanks to Francesco.